Hey everyone, and welcome back for another deep dive.
Yeah,
Today, we're going to be talking about something we all experience all the time,
yeah,
but rarely stop to think about, and that is our sense of touch.
absolutely. It's one of those senses that's so fundamental to our experience of the world,
Yeah,
but we often take it for granted. And
exactly.
there's so much more to it than meets the eye.
I mean, I think most people probably assume that touch is pretty straightforward, right?
Right.
You touch something and you feel it.
Yeah.
But there's a whole world of complexity going on beneath the surface.
Oh, absolutely. It's a whole intricate system of receptors
Uh,
and pathways and brain regions all working together to create that sense of touch.
so where do we even begin with something this complex?
Well, I think the logical starting point is our skin.
Okay, yeah,
That's really the interface between our bodies and the outside world.
right.
And embedded within our skin, we have these incredible sensory receptors called mechanoreceptors.
Mechanoreceptors.
Yeah, think of them as tiny little sensors, each tuned to a specific type of touch sensation.
Okay, so these mechanoreceptors are like the first responders of our touch system.
Exactly. They're out there on the front lines, detecting everything from a gentle breeze to a firm handshake.
So how many types of these mechanoreceptors are there?
Well, there are four main types to know each with its own specialty.
Okay, let's hear it.
But first up, we've got Merkel discs.
Merkel discs.
Yeah, and these are all about fine detail, texture, and shape perception. So think about that satisfying feeling when you run your fingers over a smooth stone or the delicate petals of a flower.
Uh-huh.
That's your Merkel discs at work. They're like the high-definition cameras of your touch system, capturing all those subtle nuances.
Okay, that makes sense. What about the other types?
Right, well, then we have Meissner corpuscles.
Okay.
And these are all about light touch and detecting movement across the skin.
Okay.
So imagine a feather brushing your skin or that feeling of your clothes moving against your body as you walk.
Right.
That's Meissner corpuscles in action. They're also really important for grip control, helping us adjust our grasp on objects as they slip.
So they're the reason we don't nub our phones every time we text.
Exactly.
It's pretty important.
Yeah, very important.
All right, what about the other two?
Okay, so Ruffini endings are a bit different. These receptors are sensitive to stretching of the skin.
Okay.
So think about bending your fingers or stretching your arms.
Uh-huh.
Ruffini endings are constantly providing feedback to your brain about the position of your limbs and joints,
Interesting.
helping you move gracefully and maintain your balance.
Wow, so they're like the unsung heroes of our touch system.
Exactly. They're working behind the scenes to make sure we don't trip over our own feet.
Okay, last but not least, what about those Pacinian corpuscles?
These guys are the deep pressure and vibration specialists.
Okay.
So think about the rumble of a motor, the thud of your feet hitting the pavement when you run, or even that satisfying click of a keyboard.
Right.
Those are all sensations picked up by Pacinian corpuscles.
So they're like the Y-angle lens of our touch system, capturing those bigger picture sensations.
Yeah, that's a great way to put it.
It's incredible how each of these receptors plays such a specific role.
Yeah, it really is.
But once these mechanoreceptors detect a touch, what happens next?
Right.
How does that information get from our skin all the way to our brain?
Well, it's quite a journey. It's like a
Yeah.
relay race with the baton being passed from one neuron to the next.
Okay.
So when a mechanoreceptor is stimulated, it sends an electrical signal along a sensory neuron, and this signal travels first through the peripheral nervous system, which is like this vast network of nerves extending from your brain and spinal cord to every corner of your body.
So it's like a superhighway for sensory information, carrying those touch signals from our fingertips to our toes and everywhere in between.
Exactly. And once those signals reach the spinal cord, they're relayed up to the brain where the real processing begins.
And where in the brain does all this touch information end up?
Well, the ultimate destination is the somatosensory cortex.
The somatosensory cortex.
Yeah, it's a specialized region in the parietal lobe of your brain.
Okay, so the somatosensory cortex is like mission control for touch.
Exactly.
It's where all those signals from our mechanoreceptors get analyzed and interpreted.
Right, and the way this information is organized in the somatosensory cortex is fascinating. Have you ever heard of the homunculus?
I have, but I have to admit I don't really understand what it means. Can you explain it?
Of course. So imagine your brain as a bustling city
Okay.
with different districts dedicated to specific functions.
Oh,
The somatosensory cortex is like the central post office receiving and sorting all the touch-related mail from every corner of your body.
okay. I'm following you.
But here's the twist. The size of each mailbox in this post office isn't proportional to the actual size of the body part it represents.
Wait, so you're saying that areas of the body with more touch receptors have a larger representation in the somatosensory cortex?
Exactly. Think about it. Your hands and face are incredibly sensitive to touch, right?
Right.
They have a much higher density of mechanoreceptors compared to, say, your back to your legs.
Yeah, that's true.
So on the homunculus, the hands and face appear grotesquely large,
Wow.
while other body parts are proportionally smaller.
So it's like our brain is saying, hey, those hands and that face are super important for interacting with the world.
Exactly.
So let's dedicate a lot of brain power to processing those touch signals.
That's it.
That's amazing.
It is the homunculus is a visual representation of this sensory prioritization. It highlights the importance of certain body parts for touch sensitivity and dexterity, especially for tasks that require fine motor control.
This is mind-blowing. But I have a question.
Sure.
We've been talking about touch as if it's just about pressure and texture.
Uh-huh.
But what about temperature and pain?
Right.
Are those sensations also processed by the somatosensory cortex?
That's a great question. And while the somatosensory cortex is the main hub for touch, temperature, and pain, are processed a bit differently.
Okay, so walk me through it. What happens when we feel something hot or cold, or when we experience pain?
Well, instead of mechanoreceptors, we have these free nerve endings in our skin that act as receptors for temperature and pain.
Okay.
Think of them like little alarm systems constantly monitoring your skin for potential threats.
So they're like the bodyguards of our skin, always on the lookout for danger.
Yeah, that's a good analogy.
But how do they know when something is too hot or too cold, or when we're in pain?
Well, for temperature, we have specialized receptors called transient receptor potential channels, or TRP channels for short.
TRP channels.
Yeah, these are like tiny little thermometers embedded in your skin,
Okay.
each sensitive to a specific temperature range.
So some TRP channels are shouting hot while others are yelling cold, depending on the temperature they detect.
Exactly.
That's pretty cool.
It is, and when it comes to pain, things get even more complex. We don't have distinct receptors for different types of pain. Instead, pain signals are generated when these free nerve endings are activated by tissue damage or potential harm.
So it's like a general distress signal saying, hey, something's wrong here. But how does the brain know if it's a sharp pain, a dull ache, or a burning sensation?
That's where the pattern and frequency of nerve impulses come in.
Okay.
It's like a code where the brain interprets different patterns of signals as different types of pain.
So it's not just about the presence of a signal, but also about the rhythm and intensity of that signal.
That's right.
That's fascinating. But how do these pain signals get from those free nerve endings to the brain? Is it the same pathway as the touch signals we talked about earlier?
It's a similar journey, but with a slightly different route.
Okay.
Pain signals also travel through the peripheral nerves and into the spinal cord, but from there they take a pathway called the spinothalamic tract, which is like a dedicated pain highway in the spinal cord carrying those signals up to the brain.
Oh, so there's a specific lane on the neural highway just for pain signals?
Exactly.
But this raises a question. If both touch and pain signals travel through the spinal cord, why doesn't everything we touch feel painful?
That's where the gate control theory comes into play.
Okay, tell me more.
It suggests that there's a sort of gate in the spinal cord that can either allow or block pain signals from reaching the brain.
Wait, so you're telling me that rubbing my arm when I bump it isn't just a comforting habit, it's actually manipulating my pain signals?
Exactly.
That's wild. How does that work?
Well, the gate control theory proposes that this gate can be modulated by other sensory input like touch.
Okay.
So when you rub a sore spot, you're essentially flooding the spinal cord with touch signals, which can compete with and dampen down the pain signals.
So it's like a sensory traffic jam where the touch signals are blocking the pain signals from getting through.
Yeah, that's a great way to think about it.
That's such a clever system.
It is the body's way of managing pain.
But this whole idea of pain modulation raises another intriguing question.
What's that?
What about phantom limb pain?
Ah, yes. Phantom limb pain is a fascinating phenomenon where people who have lost a limb still experience sensations, including pain in the missing body part.
Right? It's like the brain is still holding on to the memory of that limb even though it's no longer there. But how is that possible?
It's not fully understood, but it's thought to be related to the brain's remarkable ability to rewire itself even after a limb is lost. The brain may still have a representation of that limb on the somatosensory cortex, that homunculus we talked about earlier.
Right.
And sometimes this area of the brain can become activated, leading to the perception of sensations, including pain in a limb that's no longer there.
That's both incredible and a little bit spooky.
It is.
It really shows the power of the brain to shape our experience even in the absence of physical input.
It's a testament to the brain and incredible plasticity, but it also highlights the challenges we face in understanding and treating chronic pain conditions.
Well, this has been a whirlwind tour of our sense of touch.
It has.
We've journeyed from the skin surface to the depths of the brain, uncovering the amazing complexity of this often overlooked sense.
And we've only just scratched the surface.
But we're just getting started.
There's so much more than explore.
Yeah.
From how our brains interpret different textures to the fascinating role of touch in our social and emotional lives.
I can't wait to dive into that.
Me neither. Welcome back to our deep dive into the fascinating world of touch.
We've been on quite a journey so far, haven't we? From those tiny sensors in our skin
Yeah.
to the mind-boggling homunculus in our brains.
It's amazing to think that all this complexity is happening every time we interact with the world through touch.
You know, one thing I've been wondering about is how we actually perceive different textures.
Right.
I mean, how do we know if something is smooth or rough, soft, or hard?
Yeah.
It seems so effortless, but I'm sure there's a lot more to it than meets the eye, or should I say the hand.
You're absolutely right. It's not just one type of receptor shouting, hey, this is rough.
Right.
It's a beautifully orchestrated symphony of signals from multiple receptors, each contributing a unique piece of the puzzle.
So walk me through it. What happens when we say, run our fingers across a piece of sandpaper?
Okay, so imagine this. As your fingers glide across that rough surface, your Merkel discs are firing off signals like crazy, providing high-resolution details about the grit and the texture.
Okay.
At the same time, your Meissner corpuscles are sensing the subtle vibrations as your skin moves over the bumps and ridges.
So it's like a duet between those two receptors, one providing the fine details, the other adding that dynamic element of movement.
Exactly, and if you press down a bit harder, your Pacinian corpuscles might join the party, giving you information about the overall firmness of the sandpaper.
So it's a full-on sensory orchestra, each receptor playing its part to create that rich experience of texture perception.
That's a great way to put it, and just like an orchestra needs a conductor, our brain needs a way to integrate all these signals from different receptors, and that's where the somatosensory cortex comes in, acting like a maestro, taking all this incoming information and weaving it together into a coherent perception.
It's amazing how the brain can take all this raw data and transform it into something meaningful.
It is, and it's not just about texture. Think about how we perceive shapes through touch.
Right.
It's not just passive reception, it's an active exploration.
Right, we use our hands to trace outlines, explore contours, and get a feel for the overall form of an object.
Exactly.
It's like our hands are gathering data points, and our brain is constructing a 3D model in real time.
Exactly, and this active exploration relies heavily on another amazing sense. We have proprioception.
Proprioception. Now, that's a word I haven't heard in a while. Remind me what that is again?
Proprioception is essentially our sense of body position.
Okay.
We have special receptors in our muscles, tendons, and joints that are constantly sending signals to the brain about where our limbs are in space and how they're moving.
So it's like an internal GPS system for our bodies.
It is. Without proprioception, we'd be constantly bumping into things, fumbling with objects, and generally having a hard time coordinating our movements.
It's amazing how all these senses work together seamlessly, isn't it?
It really is.
But I have a question, and we've been talking about how accurate and reliable our sense of touch is. But I've heard that it can be tricked just like our other senses.
That's right. There are some fascinating tactile illusions out there. One of the most famous is the Aristotle illusion.
The Aristotle illusion.
Yeah. Have you ever tried crossing your index and middle fingers and then touching a small object like a marble?
I think I have, but it's been a while. I'm doing it right now. Wait a minute. It feels like I'm touching two marbles, but there's only one.
That's the Aristotle illusion in action.
Whoa.
Your brain is used to receiving touch signals from those two fingers from opposite sides of your body.
Right?
So when you cross them, the brain gets confused and interprets the single touch as two separate touches.
So it's like a little glitch in the matrix of our perception.
Yeah, you could say that.
But it's a harmless glitch, right?
Absolutely. Tactile illusions are mostly just fun curiosities that highlight the complex interplay between sensation and perception.
I'm curious, are there any other tactile illusions out there that mess with our brains?
Oh, there are plenty. Some create illusions of temperature, making something feel warmer or colder than it actually is.
Okay.
Others can create sensations of movement even when nothing is physically moving.
This is blowing my mind. It makes you realize how much of our sensory experience is constructed by our brains, not just passively received from the outside world.
Exactly. The brain is constantly making predictions, interpreting data, and creating our experience of reality.
Wow.
And our sense of touch is no exception.
It's like our brains are always trying to make sense of the world, even when the information it's receiving is a bit wonky.
That's a great way to put it. And speaking of wonky, let's talk about another fascinating phenomenon related to touch phantom sensations.
Ah, yes, phantom limb pain. We touched on this earlier, but I'd love to hear more about it. It's such a strange and intriguing concept.
It is. As we discussed, even after a limb is lost, the brain may still have a representation of that limb in the somatosensory cortex.
Right.
And sometimes this area can become activated, leading to sensations, including pain in a limb that's no longer there.
It's like a ghost limb still sending signals to the brain even though it's physically gone. But why does this happen? Is it just a random misfiring of neurons?
It's not entirely clear, but there are a few theories. One idea is that the brain, in its attempt to make sense of the missing limb, starts to rewire itself.
Okay.
The neurons that used to receive signals from the lost limb may start to form connections with neurons from other parts of the body.
So it's like the brain is trying to fill in the gap, but it's doing so in a way that creates these phantom sensations.
Exactly, and this rewiring process can sometimes lead to conflicting signals, which the brain interprets as pain or other strange sensations.
It's a reminder that the brain is constantly adapting and changing, even in the face of significant loss or injury.
It is, and it's a testament to the brain's incredible plasticity, its ability to reorganize itself in response to new experiences and challenges.
This is also fascinating. We've covered so much ground already, from the basic mechanisms of touch to these more complex phenomena like tactile illusions and phantom sensations.
And we're not done yet. There's still so much more to explore, like the crucial role touch plays in our social and emotional lives. Did you know that something as simple as a hug can have profound effects on our well-being?
I know we all instinctively reach for a hug when we're feeling down,
Right.
but I'm really curious to hear the science behind it.
Well, get ready to be amazed, because next up we're diving into the world of affective touch.
Welcome back to the Deep Dive. We've been exploring the fascinating world of touch, the tiny receptors in our skin to the amazing complexity of the brain.
We've seen how our sense of touch allows us to perceive textures, shapes, temperatures, and even pain, and how it can be both remarkably precise and surprisingly susceptible to illusions.
It's really made me appreciate just how intricate and multifaceted this sense truly is.
And we're not done yet. So far, we've mainly focused on the physical and perceptual aspects of touch, but there's another dimension we haven't explored: the emotional and social side of touch.
Ah, yes, affective touch. You mentioned it earlier, and I've been eagerly waiting to hear more about it.
Right.
I know we all intuitively understand the power of a hug or a comforting touch, but I'm really curious to hear about the science behind it.
Well, there's a growing body of research showing that touch is not just a physical sensation, it's a powerful form of social communication and emotional connection.
So it's not just about feeling the pressure of a hand on our shoulder, it's about the message that touch conveys.
Exactly. Think about the different types of touch we experience in our daily lives: a firm handshake, a gentle caress, a playful pat on the back, a warm embrace. Each of these conveys a different message, and our brains are wired to interpret these subtle nuances.
It's like a secret language of touch, conveying emotions and intentions that words sometimes can't express.
And the amazing thing is that this language of touch is universal, transcending cultural boundaries. A hug, for example, is a universally recognized gesture of comfort and support.
Makes you wonder if touch is perhaps the most primal form of communication, even predating language.
It's certainly possible, but beyond its communicative power, touch also has profound effects on our well-being. Studies have shown that gentle touch can release endorphins, those feel-good chemicals in our brains, reducing stress and promoting feelings of relaxation and contentment.
So there's a biological basis for why a hug can make us feel better. It's not just in our heads.
It's not, and it goes beyond just feeling good. Touch can also play a role in social bonding, building trust, and even reducing pain.
Wait, touch can actually reduce pain. I know we talked about the gate control theory, but you're saying there's more to it than that.
Right. While the gate control theory explains how touch can modulate pain signals at the spinal cord level, there's also evidence that affective touch can influence pain perception at a higher level in the brain.
So it's like a top-down pain release system where the emotional and social context of a touch can actually alter our experience of pain.
Precisely. Think about how a mother's touch can soothe a child's pain, or how holding a loved one's hand can make a painful experience more bearable. It's not just about blocking the pain signals, it's about creating a sense of safety, comfort, and connection that changes how we perceive the pain.
That's incredible. It makes you realize how interconnected our physical, emotional, and social experiences really are.
It does, and it highlights the importance of touch in our lives, especially in a world that's increasingly digital and physically distanced.
I think you've hit on a really important point. In our modern world, we're constantly bombarded with information through our screens, but we're often starved for genuine human connection.
And touch is one of the most powerful ways to bridge that gap. It's a way to remind ourselves that we're not alone, that we're part of a community of human beings who share the same basic needs for connection and belonging.
It makes you realize that touch is not just a nice-to-have, it's a fundamental human need essential for our well-being and development.
Absolutely, and it's something we should cherish and cultivate in our relationships.
Well, this deep dive has been an incredible journey. We've explored the intricate mechanisms of touch from the skin to the brain, and we've discovered the profound impact this sense has on our lives, both physically and emotionally.
It's truly amazing to think that something as simple as touch can have such a profound effect on who we are and how we experience the world.
I couldn't agree more. I hope this deep dive has given you a newfound appreciation for your sense of touch. And next time you reach out to touch something or someone, take a moment to appreciate the symphony of neural activity happening beneath the surface, the intricate dance of sensation, perception, emotion, and connection.
Beautifully put. And until next time, keep exploring.